Unit 2, Day 4. Polynomial functions of higher degrees. Sounds fancy. Polynomial functions of higher degrees than 2, like a degree 2 polynomial. Now let me slow down there. Polynomial functions of higher degree. So yesterday we did a lot of stuff, or Tuesday we did stuff with quadratics. ax squared plus bx plus c. That's a quadratic. What degree is that function, do you know? Second degree, degree 2. Because you take the highest power of x, and that tells you the degree it is. It's a second degree polynomial function. What if we had ax cubed plus bx squared plus, we just go dot dot dot, because it kind of doesn't matter after that in terms of what the degree is. That's a third degree polynomial function. That one has a name too. You know what? Like, it's not a trinomial because there's actually 4 terms if you wrote them all out. A fourth nomial, but we named them not by how many terms there are, but what the power is. Somebody said it's a cubic. Yeah. After that, we don't. They do have names. We don't really care, but yes, the fourth is quartic. Fifth is quintic. 6, I don't know. 7th, I don't know. They may have names, but we don't care. Like quintic, because it's the same root as quintuplets.
Yeah. I think it's sextic.
So it might be sextic because they're sextuplets.
Yeah. Septic.
Septic is like septic is like poison or septic shock or septic tank. Yeah, exactly. So let's just skip down and just, if we had ax to the 7th plus bx to the 6th, I don't know what the name of it would be, but it's a 7th degree. I don't know if it has a name. It probably does.
Isn't sept like septuplet?
Septuplets, I think you're right.
7.
So it might be a septic function, which is kind of funny. Yeah, and you could have an octic function maybe. You get the idea. We're not going to write any more down because whatever the highest power is. So I don't care about the name of it. I do care that you know what the degree is.
It's just dots.
It's just dots because I don't care what the rest of it is. This is cx plus d. I mean, I could write cx to the 5th plus dx to the 4th plus ex cubed. Nah.
So my mom asked me what are we learning today. I'm going to say septic functions.
Septic functions. All right, so 2 Roman numerals today, both kind of long, and then we'll do some examples that sort of cover everything. Because we're going to cover a whole bunch of characteristics of the polynomials, All right, characteristic number 1, degree. So we talked about what degree it is already. 2nd degree, 3rd degree, 12th degree, whatever. But the degree also tells you the maximum number of zeros. Remember, that's the same thing as roots and x-intercepts. So this sort of matches with what we talked about Tuesday. The quadratic always has, or at least has at most 2 answers. A cubic would have at most 3 answers. A septic would be a very long problem, but you would know that there was at most 7 degrees, or 7 zeros, 7 roots, 7 x-intercepts. And so we're not going to be finding all of those, but we can use that information to maybe guess what's the degree of that function, do we think?
1, 2, 3, 4, 5.
Yeah.
So you can
Wow, we're counting.
That's what we learned in mathematics.
Like count to 5s.
Degree at
So that's
5.
at least a 5th degree.
At least.
Yes,
Why?
Because it could go on.
because there could be, well, none of those are double roots, if you remember what double roots look like, or triple roots. You could also have imaginary roots that we don't see, because imaginary roots don't cross the axis. They do wiggle a little bit, so if this had another wiggle up there,
Spike thing on it.
it never has any spikes, never has any, like it could bounce. That's the word you're looking for. That's a double root. And so that's why we say, well, this is at least 5, because if one of these is a triple root, none of them are doubles because they don't bounce.
What would it look like though?
A triple, this is more than we want to worry about, but a triple, you know what x cubed looks like when it goes through the origin? It kind of does the wiggle thing. If it does a wiggle thing, that means it's a cubic. If it bounces, it's a double root.
Bounces is on the x-axis.
If it does like what you're saying, if it does that, that's a 3rd root,
Okay.
or a triple root. Although it could be a 5 root, or a 7 root, or a 9 root, and they would all do the wiggle thing. Same thing with a bounce. It could be a double root, or a 4 root, or a 6 root, or an 8 root. They'd all bounce.
Alright.
The evens bounce, the odds wiggle. So, back up. The degree tells you the maximum number of zeros. So if you got an x to the 5th problem, the most number of answers you'll have is 5. You hate in behaviors. In behaviors is easy. Bad memories, huh? Well, maybe we can explain it a little differently than you heard it previously and make it make sense. The in behaviors is like what's happening at the ends. Like when x gets really big or when x is really small, is it going up or is it going down? Do you remember what you look at to tell you in behavior? So you heard the.
I don't even remember.
So you've heard the term. No? Okay. There's 2 things that'll determine in behavior. First is lead coefficient. Ooh, do we know what the lead coefficient is? Yeah, look back at our examples there. The lead coefficient is A. It's the coefficient on the biggest power. So if the lead coefficient is positive versus negative, so that's our first test about in behavior. So it's really easy to look and see if it's positive or negative. What that means is, if it's positive, that means it ends high, meaning that whatever else goes on with this graph, it ends going up. So whatever else is happening, it ends up. Maybe it's crazy, maybe it's a simple parabola, but it ends high if the lead coefficient is positive. Again, it doesn't really tell you anything else about what's going on, but if the lead coefficient's positive, then we end on a high note. If the lead coefficient is negative,
Opposite. So it's down.
it ends low, ends on a low note, headed down. So again, whatever else is happening with this thing,
So would it always start from the top, like that, and go down, or does that just happen to be your drawing?
it happens to be my, well, if it's going down, that means that
Does the front side have to be?
it doesn't tell us about what the left end does. The left end might be going up, the left end might be going down.
So it's not that thing specific. It just happens to be.
It only tells us what's happening at the right end. If the lead coefficient is negative, it goes down on the right end. Again, there could be a whole sort of variety of things going on the rest of the way. So this only tells us what's going on the right end. To use a little bit of calculus type words, as x goes to infinity, so as x gets really big, right, x is left and right, what is y going to on if the lead coefficient is positive? Which way is y headed?
Up.
Up. What's a mathy way to say up? Infinity. And for ends down, that means as x goes to infinity, so as x gets really big off to the right, what's the math way to say down? Negative infinity.
What if x was just like 200?
So if x is not headed to infinity, we don't know anything about,
So you can't.
couldn't really say anything.
Okay.
Because maybe it doesn't go up until x gets to 500 or 1,000. It's really weird. I mean, we're not going to have those, but it's true that if one of your roots was, or one of your factors was x minus 500, then the end behavior doesn't start till at least 500. It's way out there.
Okay.
So that's why we have to say infinity, because we don't know. You could have a root that's at 1,000. I mean, we're not going to, but you could.
Okay.
So we just say as x, eventually, maybe that's a better way to say it, eventually y gets really big. Eventually y gets really small, based on the lead coefficient. All right, if the degree we'll make the degree be an orange issue, just for the heck of it. If the degree is, do you remember what you look at on degree? What'd you say? Even or odd. The degree is even versus the degree is odd. Now this is a little bit weird because the degree doesn't tell you the left end, at least not directly. It only tells you if it matches the right end or not, if it's the same as the right end. So if the degree is even, left end is the same as right end. So even or odd doesn't tell you up or down, it just tells you same or opposite, which seems a little bit weird. So that's why you got to know the lead coefficient first, because degree being even or odd doesn't directly tell you up or down, it only tells you same or opposite as the right end. If the degree is odd, that means the left end is opposite the right end. The O's kind of go together. That helps some people remember it, odd and opposite. So I didn't leave much room here. So that would be an even power or an even degree polynomial because they're going the same direction. that would be an even degree function because they're going the same direction.
So like a cubic parent function is odd.
Yes, and so you can use some of the stuff you already know. Like you know that a cubic is odd, and you know what a cubic looks like. Right, there's a cubic. You know a cubic is odd. The left end is doing the opposite of the right end. I could draw another cubic. I'll just draw one that's even more goofy looking. The left end is doing the opposite of the right end. Opposite versus same. So lead coefficient tells you the right end. Degree doesn't tell you left end, it tells you same or opposite. So be careful, you can't just say if it's odd that means it's down. No, odd would just mean it's opposite. So you have to find the lead, you have to use the lead coefficient first so that you know if you're talking, when you say same as what? Opposite of what? Let's look at some pictures then, some examples. And I want you to say how to phrase this. Let's do a couple pictures first. Whoops, I guess I should put that where you can see it. And you know, for this exercise, I actually don't even need the x and y axis. I could just draw the picture. So 4 pictures. Let's make a table out of this. This will work this way. So lead coefficient, and all I want to know there is, because all we could really say there is if it's positive or negative, and for the degree we'll say if it's even or odd. Let's do the first one together and then I'll leave you a few minutes to think about the next 3. So on this first picture, is the lead coefficient positive or negative? How did you know that? Because you're smart. It goes up. Alright, be careful saying it. What goes up? The right end goes up, so it's positive. The lead coefficient is positive. How about the degree? Is it even or odd? How did you know it was odd?
It's different.
Because it's different. Alright, so you work through the next 3. Again, those should be pretty quick, but at least be a little midway check on how we're doing. Alright, so there's your answers. Check those, make sure you got the same thing I did. I'm sure you did. All right, let's talk about zeros. Some more. We've talked a little bit about them. Zeros, roots, x-intercepts. All right, if the graph bounces off the x-axis, what does that mean? You remember? We just said it a minute ago.
It's second.
It means it's a double root. It's a...
So if it bounces on 0, that's when it's a double root.
It doesn't have to bounce at 0. I mean, it bounces where y is 0. It doesn't have to bounce at x equals 0.
Okay.
Double root, which means it's a double factor, which means it's a double zero. So all those words continue to go together. Although I guess we should be careful because it could be a quadruple or 6x. Well, I don't know what the word is. Or I do know what the word is and don't want to say it. I don't know. Quadruple or a 6x. It's an even power of root. So if we look at a picture like that, that's a double root.
Yeah.
There's 2 roots there.
That's a single root.
So that would be 3 roots.
So there'd be 3 roots overall, which would make it a odd, which would make it a cubic. And you look at that, and you're not super familiar with cubics, but I bet you're familiar enough with them to recognize that, yeah, that's a cubic equation. That's what a cubic looks like. A cubic has 3 roots. And this is why we say it has at most 3 roots. It depends on how you phrase that question. You can say it has 3 roots as long as you understand that some of them might be double roots.
Could it do the same if it was turned sideways but on the y-axis instead of the x-axis?
Okay, if it's turned sideways,
Would that be the same or would it be a different root?
like this kind of turned sideways,
Yeah.
that kind of turned sideways is not a function
Because the vertical line.
because vertical line test.
And this will only work with functions then?
And so we're only talking about functions.
Okay.
So you're right, like this is like some sort of double y root, but this isn't a
If
function.
it would
So
work, would that have to be how it would be?
yeah,
Okay.
so you're thinking right. We're just not going to do those because they're not functions. Let's write down some of the things you guys said because all that was good. So this is probably a 3rd degree because you got 2 there and 1 there. I said probably because we don't know for sure that that's a double root. That could be a quadruple root or a sextuple root or an 8-tuple root or a 10-tuple root. 10-tuple, whatever the actual words are. Decaroot, maybe? Imaginary roots do not cross the x-axis. Because if they cross the x-axis, they'd be real roots and you could figure out what they are. So this kind of makes them tricky to see. Like it's easy to see the real roots. It's when it crosses the x-axis. In fact, we could have said that's a double real root, and that's a single real root. So the picture of a imaginary root, well, you can see that something's going on. So a picture like that. So be careful how you phrase that. There's only one real root. But there's some wiggle going on, so there's other roots going on, but you can't like say, oh, it's right there, because it's not right there, it's imaginary. You can only say, because of the wiggle, there's some imaginary roots going on somewhere.
So you can't name the amount of imaginary roots?
Not yet with what we know.
Okay.
Like there's more to it. Like the question was, can we tell how many imaginary roots there are? Not really.
Would it be the same with the balance thing?
You can kinda. They do come in pairs, so there's always going to be 2 or 4 or 6 of them, and you could kind of go with how many wiggles there are. So one wiggle probably means there's 1 pair, but that's pretty loose. Like we're not going to test you on that because it's too hard to see exactly what's going on there. Here's a very mathy word, but I'll explain it in a minute. Weird roots come in pairs. And you're like, weird? What does weird mean? Weird means imaginary or square roots that won't simplify. Irrational. That would be the fancy way to say that. Come in pairs. Here's what I mean by come in pairs. You see this in the quadratic formula because you get plus or minus, so you end up with maybe 3 plus or minus 2i. They come in pairs. And maybe you got a square root in there, so if 3 plus 2 square root of 5 is a root, do you know what the other root would be? 3 minus 2 square root of 5. So they always come in conjugate pairs. In fact, if we really want to get... And again, working with the quadratic formula first helps us see this, because that always happens with the quadratic formula. And if your square root isn't weird, if your square root ends up being 9, then you don't have this happen. You just get two nice numbers. But if your square root ends up being -4, so you get plus or minus 2i, well, there's a pair of them. Same thing with the square roots. So they always come in pairs. All right, let's try to do some examples where we do kind of all of this stuff put together. So there's lots of information today. I don't think any of it's that hard. It's just it feels like there's 10 disconnected thoughts to make sense of. Which means there's lots of ways we can ask questions. Find a third-degree polynomial with zeros of 1, -2, and 3. Find a third-degree polynomial with zeros of 1, -2, and 3. This is real similar to the last couple on the most recent worksheet. Because if x equals 1 is a root, and x equals -2 is a root, and x equals 3 is a root, what factor would have led to x equals 1 being a root? X minus 1. So you have to think backwards a little bit. If x equals -2 is a root, what was the factor that led to that root? X plus 2 and x minus 3. And we want to make it an equation, so don't just leave it the factors there. Put f of x equals on that.
You have to solve it.
You got to multiply it out. Yeah. You don't have to solve it, because solving it would be your answers are already there. It's already been solved. You're unsolving it. So we need to FOIL that thing out. Reverse solve it. And the opposite of factor is FOIL. Not exactly, but close. So I need to pick two of these to multiply together. It doesn't really matter which two. I can't do them all at once, so let's do x plus 2 and x minus 3. So x squared minus x minus 6. And then, here's the fun part. Got to distribute x to everybody, so x cubed minus x squared minus 6x. Then I got to distribute the -1 to everybody. Minus x squared plus x plus 6. So x cubed minus 2x squared minus 5x plus 6. So this is one of those problems where the new stuff, the stuff we most recently learned, is the easy part. The old stuff is kind of the hard part, foiling, just being careful with keeping up with things. Find a fourth degree polynomial with zeros of 0, 2, and negative 3. Fourth degree polynomial with zeros of 0, 2, and negative 3. Okay, so you're right that something isn't quite right here. So what's not right, first of all, is I'm giving you 3 zeros, but it says it's a fourth degree polynomial. So if I just multiply all these out, that's only going to be a third degree. So something's missing. So there's a couple ways to solve this. One way would be, I don't think you should do it this way, but it didn't say that these were the only zeros. So you could just say, oh, I'll just put another 0 at 1 in there. It wouldn't be wrong. So let's fix it so we can't do that. With only zeros. So I can't just throw in an extra one, although that would have been right. That would have been okay before I put the only in there. It also precludes throwing in an imaginary one. So the double root, I can get an extra one by doubling up one of those.
Would it matter which one specifically?
So, great question. Would it matter which one I do? The answer is no. I mean, it would change the graph, and it would change our answers, but there are 3 different ways to answer this question. Now, since I want you to multiply it out, which one do you think would be the smartest one to put the double root on? The 0. So, yes, you could put it on any of them, but come on, let's make our lives easy here, and let's make the x squared the easy one. X squared plus x minus 6. Then distribute the x squared. So on this one, the multiplying, I think, was easier than number 1, but the concept was a little harder because of this fourth degree, and yet there's only 3 zeros, so where do we come up with the extra one? Well, if you read the question carefully, you could have just thrown in one on your own, but it would be better if you would make one a double root.
So if we choose which one was double, but if it was a multiple choice per se, if it didn't work with that one, we'd have to try with each individual.
Yeah, that would be a rough multiple choice question, because then you'd have to multiply them all out potentially 3 different times. So we would not do that to you.
Yeah.
Could you show us an example of like a third polynomial degree with like negative 1, 2, and 3?
I mean, that's basically what we did on number 1, right? Number 1, we spelled it out for you. It was very straightforward. Third degree, here's your 3 answers. You're good. Things get a little tricky when we give you 3 answers, but say it's a fourth degree, like something's not adding up. That's why we had to make one of them a double.
If you say a fourth degree and then you only give us 2 zeros, does that mean we have to double both of them, or do we
No, you could
quadruple one of them?
well, you couldn't quadruple one of them because then you'd have 5 total, but
3.
you could double both of them, or you could triple one of them and single one of them. Or you could triple the other one and single the other, so there's still several different ways to get there. So that they don't make good multiple choice questions because there's multiple right answers. But they make good free response questions because, I can give you one question and have there be 3 different answers. Find a third degree polynomial with zeros of 0 and square root of 3. So it's kind of like the last one, like, wait a minute, you didn't give me enough zeros.
Wouldn't you just square root of 3?
But we said these square roots come in pairs, so if x equals square root 3 is a 0,
just square root the 2. Wait a second, if you square root the square root 3, that just makes it a 3.
then if the square root of 3 is a 0, then what else has to be a 0? Negative square root of 3. So this one there is only one other answer. Or there is only one answer. You don't get to double something or make one up. You have to know that these two come in pairs. Foiling. But watch what happens when you FOIL with conjugates. We've seen this before already a couple times. What happens when you FOIL with conjugates? Yeah, the middle terms cancel out. So you can write them out if you want to, but they're going to cancel out every time. And then if we'll distribute that x cubed minus 3x.
Would you ever give us x cubed minus 3x and tell us to find the zeros?
Yes, I could do that, because you would factor out an x first, and then you could do, well, you wouldn't really factor what's left, but you could use the square root method to come up with 2. So the question was, would I ever give you this and ask you to find the zeros? Yes, for that one. Generically, would I give you a higher power polynomial and ask you to find the zeros? Only if it was possible. So I would not ask you to find the zeros of x cubed minus 4x squared plus 7x minus 12. Because what are you going to do with that? Like, there's nothing to do. You're stuck. So if we give you one that's higher power, it will be something that you can factor and kind of break down. So you're right to be concerned, but we'll make sure that it's possible. 2 more examples. Almost there. Find a third degree polynomial with zeros of negative 3 and negative 2i. Find a third degree polynomial with zeros of negative 3 and negative 2i. Yep, so that's an imaginary. That means there's a pair that goes with it of plus 2i. And that's why we only needed to give you 2, because that imaginary one sort of has an automatic partner that goes with it. So x plus 3, x plus 2i, x minus 2i. It's going to be a yucky one again. Although there should be some canceling going on, so x squared plus 2x or plus 2ix minus 2ix will go away. So I'm not going to write it out this time. We've done enough of those. O and the I cancel out. What's 2i times negative 2i? Negative 4i squared.
And so that becomes
And right, the I squared is negative 1. So that becomes plus 4. And then I need to FOIL that out. So let's see, x cubed plus 4x plus 3x squared plus 12. So here's a question on this one. Crystal, you could ask the question now, would I give you one like that and ask you to find the zeros? And the answers would be no. Because what am I supposed to do with that? Actually, I could do that one because you could group it and solve it. So I could give you that one. If I give you one and ask you to solve it, you will be able to solve it.
But will you?
Well, you should be able to solve it, I guess I should say.
It can be solved. But maybe not by us.
Speaking of that, you guys are reading my notes here. Last one. F of x equals negative x to the fourth plus 16x squared. Well, hold on. Let me give the instructions, but you are going to pull out the x squared. Let's find the zeros first. I'm okay pulling out an x squared, but it might be better if we pulled out a negative x squared, just to make life a little easier down the road. I'm going to...
Oh, yeah, I guess you could just...
Well, let's factor. We're less likely to miss the plus or minus thing. So what are my zeros? Good. 0. Some people miss this one. They just overlook that. X equals 0. X equals negative 4. And x equals 4. Something's not right here. How many zeros was I supposed to have? So what's going on? Why does it look like...
No, wait, no.
What's going on here?
There's
not an imaginary 0 because it would have shown up and they would come in pairs, so that would mean we'd have 5.
Because the x squared is all squared.
That squared means that this is a double root, is 2 zeros. Which means it'll, on the graph, it will bounce there. Part B, in behavior. So, like, what's the right end doing?
It's going to be doing the coefficient.
All the way back to the first thing we said in here today.
The coefficient's on the outside of the first one.
The coefficient is the lead coefficient.
It's going to be negative, so it's going to go down.
Is going down because lead coefficient is negative. What about the left end? It's degree 4. So it has an even degree. What does even degree mean?
It's going to go the same.
The same. So down, but it's not like directly down. It's because it's down because it's the same as the right end. Now let's sketch a graph. So we have a 0 at 0. That's a double root, so that's going to bounce. A 0 at 4, and a 0 at negative 4. The right end is going down, so after we go through 4, we got to be going down. The left end is going down, so after we go through negative 4, we got to go down. And we have to bounce there, and we have to cross at those two, so those are crossers. And so I have to turn around somewhere, head back, bounce. So it looks something like that. Because I have 4 sort of zeros, because one of them's a double. These two are crossing zeros, the other one is a bouncing 0. Alright, worksheet is worksheet 4. Oops, Unit 2, worksheet 4. And again, due tomorrow are worksheets 1 through 3. That should already be done.
Just about done with them already.
Hopefully mostly done. We'll see. We still have like 20 minutes in here. So you can definitely have time to finish worksheets 1 through 3. I will take them today. If you're done and you want to hand them in and just be like, I don't want to worry about it. That'll work. Or I'll just take them tomorrow. Your choice.